So you get some clever thing here where you're able to see, two Zoom calls, I guess, like the one with me and then the one with everyone else who's at least tuning in and slowly.
Yeah, although I can't see. I think most people have. I don't think anyone. I can only see who's tuned in as a moderator. I can't see any of our listeners.
Ah, okay.
Yeah.
Right. So it's a one-way screen.
Yeah, it's a one-way screen. Maybe first of all, do you maybe want to check whether you can share your screen?
Yes. Let me. It pops up, and I can do that.
Great.
Looks like we're seeing my screen.
Yeah, I see you. We're seeing your screen.
And if I do that, we're in. And
yeah.
just to check, can you see the mouse?
Yeah, I can see the mouse.
All right, cool. Right, should I close?
Well, let's maybe give it sort of another minute or two, and then I think we're good to go.
Cool. I mean, yeah, I can keep it on this screen, or I can move back. But yeah.
No, that's fine.
Need to decide where best to leave the little thing of us. It was quite amusing. So I set up here to sort of get ready to go, and then realised I was in a really dark room, so I had to sort of root around and find some lamps, because I thought it's probably not the best way of presenting if you just see me,
yeah.
darkness, and it doesn't come across too friendly.
So maybe well, we've now got 15 participants. Let's maybe wait another minute.
Cool. I've definitely given presentations to smaller rooms before.
Yeah, because we organized this very last minute. I'm surprised that there's 16 people. That's a decent turnout.
Yeah, double digits. I won't complain. Yeah, just let me. I'm happy to keep waiting. It's really not you just let me know when you want it to
I think I think, to be honest, I think we can get started. I'll do a very quick introduction. So yeah, thanks everyone for tuning in, and welcome to our second last event of term. So we're here with Oxford Quantum Circuits, specifically with Dr. Jonathan Burnett, who will give us a presentation about quantum hardware. So Oxford Quantum Circuits is a local company at the forefront of building a quantum-powered future to enable groundbreaking advances in computation. And Oxford Quantum Circuits quantum computer is actually the first completely functional unit, which is currently commercially available in the UK, called the Coaxmon. And Dr. Jonathan Burnett is Oxford Quantum Circuits head of quantum hardware, and he'll tell us about their quantum computer, and will hopefully answer any of your questions after his presentation. And Jonathan works with the quantum hardware team to advance Oxford Quantum Circuits experimental efforts. Specifically, he oversees developments across the device design, fabrication, the cryogenic setup, measurement, and reporting. And prior to joining Oxford Quantum Circuits, he worked in the National Physics Laboratory, and also he worked at the Wallenberg Center for Quantum Technology in Sweden, and prior to that also worked at the London Center for Nanotechnology. So thanks so much for taking the time and joining us, Jonathan. Yeah, I'll hand over to you, and feel free to get started.
Thank you very much for the nice introduction, Jan. Yeah, so when you sort of hear all this said back to me, it makes me feel quite old. Yeah, so yeah, indeed, I'm Jonathan Burnett, and I'm the head of quantum hardware at Oxford Quantum Circuits. I think a huge thank you to Jan and to the rest of the kind of Quantum Information Society at University of Oxford for first reaching out to Oxford Quantum Circuits in general and asking if we'd like to give this presentation. And then that kind of conversation went on, and then I got the opportunity, and here I am. So thank you very much for allowing this to happen.
Yeah, it's our pleasure.
Yeah, no, it's cool, really cool. Thank you. Yeah, so here I'm going to try and talk about basic scalability of superconducting circuits, and in particular focus on the Coaxmon, which is a design that's come out of the Leak Lab at University of Oxford and is now the kind of core technology for Oxford Quantum Circuits. So just to give an overview, so this will be about a half-hour talk. This is going to go over kind of a little bit of history on OQC, the company, a little bit more on me, slightly focused from like a kind of maybe a careers perspective. Just thought this might be of interest to any kind of undergrads or postgrads who are kind of wondering about working in the quantum computing landscape. Then moving on to kind of superconducting circuits, how these were traditionally handled, how scaling normally worked, with kind of branching into how the Coaxmon as a design addresses a number of these things, before finally kind of working back to this, working in quantum computing as a whole. So just again, just some kind of background, kind of careers ideas, just maybe might sort of plant some seeds or answer questions that maybe people didn't even know they had. And then indeed we'll move to a question and answer session. I can't promise to be as bold as Jan said. I can't promise I'll answer all questions. I will do my best, and hopefully that will be good enough. Right, so with that, on to Oxford Quantum Circuits. So this is a company that originally started within the Leak Lab. So Peter Leak, a lecturer at Oxford University, founded this company. He runs a very large academic group in the UK, certainly large by UK academic standards. Started this company in 2017. The next slide will confirm that. But now the company is ran by Ilana Wisby and Claire Blett. So Ilana is our CEO, in charge of kind of company strategy, keeping us going forwards, kind of really instilling visions on kind of what a modern company will be in this kind of quantum landscape. And of course, on top of them, or not on top, but with they're giving the leadership, but the rest of the team is now 17 employees. So I think that makes us a small, medium company now, no longer a mini one. And this is a whole assortment of people. So in order to try and make a quantum computer, you don't just need people that know quantum physics. You need an assortment of people that know a lot of software skills, things like programming FPGAs, people who are good at nanofabrication. You need hands-on physics skills as well as sort of simulation work and kind of more theoretical aspects. So it's a pretty sort of diverse set of skills that the company as a whole has to have. And as the company grows, it needs to keep kind of finding more and more people that can fit in and kind of keep adding something new each time. So that's quite nice to sort of work in somewhere that's sort of that kind of dynamic in a way. To kind of move on to the company story a little bit. So indeed started in 2017, originally as something which was hosted within the Leak Lab. So there were a lot of facilities and some people, some PhD students and some postdocs were basically paid for via the company. This led to a number of kind of initial demonstrations, which all occurred basically within the Leak Lab. Then there's some history of kind of more money coming in through Innovate UK grants, moving on to some partnerships with kind of key players. So Riverlane being, I believe they actually gave a talk last week or the week before. So I think you've been introduced to these, but they're kind of at the cutting edge of the software development relating to a quantum computer. Again, tying into this sort of picture that you need a very diverse set of skills, and there's numerous facets to even how do you approach quantum computing, and one of them is entirely software focused, as Riverlane.
Quick interruption. Yeah, we had Riverlane last week, and even if you missed the talk, it will probably go online on our YouTube channel, so you can listen to that if you missed it.
Awesome. Yeah, so indeed partnering with these because of trying to basically partner with the best, and they are indeed very good. For me, this sort of moved to something which is probably most interesting, which is this movement to a new lab. So in November this year, that's this month, at the very beginning of this month, we finally moved into our kind of new laboratory to get up and running. This hopefully would have happened earlier this year, but there may have been a global pandemic going on, which does affect a few things. So what's the kind of idea that OQC have? And really this kind of boils down to, I think, quite a simple principle, and it's one that I like. And this is that you don't want to just compete only on kind of qubit numbers. So this sort of brings us to this scalability point, which is going to be a kind of key part of this talk. If you only fight on numbers, you're really kind of going for a quantity over quality argument. And in actual fact, you need both. So you need to have a large number of qubits, but you need their performance to never degrade. You always basically need to make sure that in the end, you can perform some very deep algorithm, meaning many qubits, many operations, but you also need the fidelity of that deep algorithm to be high, which is ultimately saying you need the quality to be high. So for this reason, some of the kind of estimates that have come out from certain companies on things like thousands of qubits and this kind of thing, this is I think a little bit too moved away from actual practical applications, things that you can do on smaller numbers. Then in terms of the kind of approach and what we'll be talking about is actually going to be superconducting circuits. So in general, for building a quantum computer, there's many technologies you could use. Some of these have pros and cons. At the moment, the two leading candidates are either trapped ions or superconducting circuits. These have certainly showed the most promise, both academically and probably commercially within the last sort of 10 years or so. These certainly commercially, most of the big players are using a superconducting circuits approach, and this is what OQC are also using. And the normal arguments which are kind of put forward as to why this is a good idea is that you're using things which you can make within a clean room that was built upon semiconductor technology, and that the kind of wavelengths of superconducting circuits, you often make things work at microwave frequencies. That means you're talking things which are millimeters in size, and this is a whole kind of frequency space that, again, we're sort of very familiar with, and this is already well developed through radar technologies, same with your mobile phones and so on. So that's some of the reasons why superconducting circuits are normally touted as being a very promising approach for this. Now let's move to just a little bit about me. I don't plan to repeat everything here. Basically, what I sort of thought I'd put in from this is that I started with what you might call kind of a traditional academic background, so a physics undergrad or a 4-year master's course, going into a PhD and research there. And this was always relating to superconducting circuits, this research, but at some point I sort of pivoted towards a government lab / semi-commercial basis, and then basically this year took the kind of full step into a commercial operation on trying to make a quantum computer. And this, I think I just wanted to emphasize, this isn't the only way. So lots of people come into this in a similar background. So basically meaning a physics or computer engineering or electrical engineering type background to then go into research and then sort of pivot across. But ultimately, if everyone's doing that story, then it does mean we're not necessarily going to get the kind of diversity of thought and diverse teams that you ultimately need to kind of build this thing together. So while this approach has worked for me and is something people can follow, it really isn't the way. And I'll sort of touch on this again at the end with just some sort of questions of do you have to have done a PhD in order to get into this game? And the answer's yes and no, but for different reasons. So let's move that down to there. I think it's now out of the way. Right, now to sort of talk through some language. So I want to sort of make at least what I will define as a difference between infrastructure and architecture. So what I'm going to here define as infrastructure is kind of quite nicely captured in this picture. So this is a picture of when the Quantum Information Society visited Leak Lab in February this year. What you've got here is you've got here's a laboratory, and you've got obviously a bunch of people. So we've got some of yourselves visiting, and we've got Peter Leak here on the side. What you can also see in the background are these kind of table-like frames, and these are sort of what I'll talk about, which is that these white cylinders within this are what we call dilution refrigerators, and these are what we require to actually handle the cryogenics that does the cooling to get our qubits down to 10 millikelvin, which is where they operate. And the point I sort of just want to make here is that basically these things are people-sized. Quite literally, they are as wide as the sort of typical person's shoulder span. Some of them can be wider. These are a kind of common technology which you can buy commercially. There's several kind of people that companies that sell dilution refrigerators, and they are common to most of the approaches for quantum computing. So whether you're using a spin-based platform, quantum dots, or superconducting circuits, all of them would require you to have a dilution refrigerator. And this kind of ties into a kind of key point, which is that quantum computers are not portable. There's a reason why a lot of companies in the end sort of look at partnering with kind of web-based cloud services, and that you sort of have to think of this in terms of a supercomputer, which again is something which is not portable, right? The access to them is portable because it's done via the cloud, but the machine itself is not. Equally, for trapped ion qubits, while these do not typically have cryogenics, they often do use vacuum systems and optical tables, which are again of a similar size. But here, the point I sort of want to make is that I'm going to say that infrastructure, for the sake of this talk, is going to mean all the things within the lab. And while scaling is in some way related to infrastructure, because ultimately how many things you can fit inside of this cold volume is going to create some hard limit for you. At the moment, that's not really going to be the content of this talk. So instead, I'm going to talk about what I'm going to call architecture, and this is going to mean almost maybe in like a kind of Lego plugging bits together. What bits do you need in general to make a kind of quantum computer if we sort of build this up? And then I think the kind of standard example here would be probably to work with these Coaxmon style qubits, which have come out of UCSB, the Martinez group, and is now used by Google. So what you're seeing is kind of four key components here. The first is we've got this microwave transmission line, which is this horizontal coaxial sort of strip here. Then you've got this meandering structure, which is a resonator. Finally, you've got the cross, which is the Coaxmon style qubit. And then right at the bottom, you've got these very thin lines, which are again a microwave transmission line, but this is actually a qubit signal line. So this is where you send the signals to each qubit. And in terms of what these are sort of meant to do and not do, we have that the resonators are meant to couple to qubits. So that's what these sort of C-shaped couplers are. And they're only meant to couple to the qubit with the C. So this resonator here should not couple to the diagonal one. It also should not couple to the adjacent resonator. Likewise, our qubits are meant to then, the coupling's two-way, so they're meant to couple back to the resonator, and they are meant to couple to their adjacent, in this case, nearest neighbor qubit. However, they're not meant to have this diagonal coupling back to the other resonator. So in this case, when I'm sort of saying things should not exist, ultimately that means that if you've got too much of a coupling here, you will, in the end, kind of create infidelities, and you'll create kind of problems as you attempt to scale this circuit. Just to then sort of make a kind of general point, which is that I'm talking here kind of, this sort of bold text is like the components that you need, but they don't always look this way. So sometimes, your resonators can be 3D cavities instead of quarter wave resonators, or coplanar in this case. It could be a literal lumped element. So you could look at it and think that really looks like there's a capacitor and an inductor there. Or they could be coaxial, like the Coaxmon that we'll get to in a moment. Likewise, the kind of qubit coupling is currently nearest neighbor on this example, but there can be a transmission line in the middle, which looks like a microwave bus, or there could be another qubit, which is acting as a tunable coupler that you can kind of bring in and out of resonance with the two qubits. So again, there's just different ways that this can look. In terms of how does this scale, if I kind of cut away one of those images, I could sort of make this argument that what you're seeing is sort of like a unit cell. So basically, you've got a bit of this microwave transmission line, one resonator, one qubit, and a local drive. If I consider all of them to be a unit cell, then in that case, this is going to scale in one dimension. So you kind of get to what I showed in the previous, which is I can kind of repeat this pattern, just continually adding one to the right, and this is a 1D scaling. And this is indeed what the field was doing about 5 years ago, where you had a number of kind of demonstrators, again, coming from UCSB, the Martinez group, where really they kind of worked their way through, here's one qubit, here's two qubits, here's 5, here's 9. And what you can see is that while, I think I now want to put this up here, sorry. While this sort of is scaling, they were able to sort of show that you can start doing interesting things and manipulating larger and larger quantum systems. It does have its problems. So one problem is that actually, if you wanted to couple, the leftmost and the rightmost qubit, you had to go through all of them because it was nearest neighbor only coupling. Another is that what you can see here is that these microwave signal lines have to start fanning around the edge of the chip, which means that I've got this sort of strange thing going on where the number of qubits I can scale is in some way proportional to the perimeter of the chip. And that's a really strange thing to sort of have, and it's not something that you'd normally comment about, except that even as you see this picture, you can already see at 9, they basically couldn't go any further. So in order to go further, you have to sort of fundamentally, start making some really big design changes, and those design changes can have some repercussions. So now we want to sort of work through, what those repercussions might be. This means we have to sort of think a little bit about qubit performance. So the typical way of thinking about qubit performance is to look at what's called the longitudinal relaxation, or the qubits T1. In order to think about this, you normally think of the qubit states on a block sphere. So that's the gray sphere as shown. And in that case, the two poles, so the North Pole and the South Pole, you would normally equate to thinking of the qubit being in a 0 state or a 1 state. In this case, the 0 is the ground. So if you do nothing to the qubit, your representation of the qubit state is a basically pointing northwards. What we can do is kind of manipulate the qubit from this orange path. We can sort of send a pi pulse, which will send it from 0 to 1. So it will kind of follow that dashed line on the orange. Now the qubit's pointing in the 1 state, and we can wait some amount of time and see how long does it take for the qubit to relax back up to the 0 state. So kind of schematically, you can see what this would look like is that we send one pulse shown here on this little green rectangle, saying this is me flipping the qubit from 0 to 1. I wait some amount of time tau, which is equal to this x-axis on this plot. We then perform readout and ask what state is the qubit in? Is it still excited and in the 1? Is it, because this is a probabilistic measurement, you have to do this many times over. You're basically seeing what number of times was the qubit still excited. And so what we see is that at very short times, the qubit's basically always excited. At very long times, it's basically never excited. This is then following an exponential decay, which has a time constant of T1. And this is what we then call the energy relaxation rate. So in other words, how long does energy remain within the qubit before it dissipates? Like most kind of ring downs, you can equate this to a quality factor. So here we just need to know what is the qubit's excitation frequency in order to do that. So then it's kind of obvious to sort of move on and think, now we've defined performance, now we need to get an idea of what is good performance, what do we consider good. For this, you can see many examples of a plot like this, where on the x-axis we've got year, on the y-axis we've got this T1 time. The normal argument when this is presented is that you say this is an upwards trend, and this is therefore saying superconducting qubits are a really sensible platform to use. That statement's completely fine, but there are a few bits behind the scenes going on here. So a key one is that what people will normally say is that the benchmark is to hit 100 microseconds. Work that into a quality factor, that's saying 3.5 million. That quality factor you could now compare to things like natural atoms themselves, and you'll see that they actually have a similar quality factor. In which case, this again is an argument for saying, look, you've got this engineered man-made system, and this performs as well as nature does when it makes an atom. And that's actually quite a powerful statement. However, some of these other things here, what I think are worth mentioning. So one is that all of these data points on here correspond to a single uncoupled planar qubit. That means a one qubit only that's measured. It means that qubit is not coupled to any other qubits. And it also means that the technology from a scaling perspective is exactly what I kind of showed on about 3 or 4 slides ago. In other words, none of these demonstrations really hit these numbers or show that you're hitting these numbers when you take scaling seriously and start to alter the design in a way that scales. And just to sort of mention a final point here, the reason why this is normally used as the metric is because an approximate way of understanding how many operations you can perform is to look at the ratio between T1 and the gate duration. And basically, this leads to a very simple conclusion, which is that anytime you want to sort of ask, how do I make deeper and deeper algorithms, so more operations, you will always come back to the answer that says, well, you need to make better qubits. So doesn't mean you can't do useful things in the meantime, but is always a reason why companies and academic groups and the entire community have to care about, how do I make better qubits. So let's now, so let's put that back down. Now let's start thinking about how was scalability introduced in traditional designs. So one route is to include things like air bridges. So this is an example that you see here, where what you've got is literally this bridge-like structure. This is now enabling you to kind of make a galvanic contact from one end to the other. And importantly, it's enabling you to cross paths. So if you sort of remember this example I showed of the wiring fanning out on these planar chips, it's fanning out and running parallel to other paths the whole way because no lines are able to cross if you're doing something in a planar way. Another example is that you can include what are called vias. So normally this is actually called a TSV, meaning a through silicon via. You get a kind of idea on this schematic here at the bottom. So this is a way of routing a signal from one side of a chip to the top side of the chip. So it's represented by this continuous line. And then the final part, which is pretty much always used by most companies, normally with a combination of one or both of the other two, is what you call flip chip. So this now means that you're creating what's referred to as a multi-chip module, because you've now taken basically two different chips. So one of them is being called here the interposer, the other is being called the qubit chip. And quite literally, the qubit chip is being flipped upside down and placed on top of the other chip, hence why it's called flip chip. And the key thing here is that you have to make a signal connection which is low loss, and therefore you use an indium bump bond, as indium is a superconductor. This is, for example, exactly what was used on the quantum supremacy example. So here you've got the qubit chip, which is now facing down, so the qubits are no longer on top. And then here's the interposer. A key feature here, though, is that the wiring is still fanning out. Right? All of these straight lines are all still corresponding to ultimately wiring that's fanning out to the edge of this chip. So in this way, although the scaling's definitely improved, because this was a 53 qubit device, you still do have some slightly strange constraints. The relevant thing, however, is to ask the question about performance. So in this case, the MIT group have measured this, and they're pretty much sort of leading, at least in terms of groups which are publishing this stuff still, of making, and you'll note, sorry, this is the same paper as gave this schematic example. They measured the T1 of their flip chip devices and basically find that this T1 is actually very low. It's nowhere near the 100+ microsecond number, which they can otherwise demonstrate. And for me, this really isn't surprising, because in order to go about making a multi-chip module, you do have to do a lot more additional processing, and you ultimately encapsulate your qubits in a additional dielectric environment, which are all things that the community basically spent 10 years from sort of 2000 to 2010 learning was a bad idea, and learning that these were things that would limit your device performance and you shouldn't do them. So it sort of feels to me like this is an example of sort of not learning lessons, or at least learning lessons and then realizing you have to change the approach so fundamentally that you can't carry it forward. So with that, we'll sort of now move on to the Coaxmon and how this approaches things in a similar but different way. So what you've got is this schematic on the top left side. So the gray is an example of your chip, so silicon or sapphire piece. Working on the green first, so this is now on the bottom of that chip. You've got this sort of ring and circle. So this is picked so that it looks coaxial. Coaxial basically meaning like a coax line, like a coax wire. So something where you have a central signal line and then on the an outer ground, basically. So what you've got here is a kind of inductive spiral, and then you otherwise will have some capacitance between the central island and the ring that goes around it. This will form the LC resonator, and you access this via a measurement port on the bottom. That measurement port is now coming vertically. So just to begin with, this is from the very beginning, this is a vertical connection. In other words, it's an out of plane wiring. To now work to the blue shape. So again, this is kind of now aligned so that it's sitting basically on top of the LC resonator, but on the top side of the chip. And now again, you've got this outer ring, you've got this inner dot, but now the connection is by a Josephson junction. The Josephson junction is what creates the anharmonicity. So in other words, this is a nonlinear inductor. So in this case, just to sort of give some idea of numbers, what you have here is that the resonator, so the green part here, has a resonant frequency which is about 10.23 gigahertz in this example. I'm sorry, the paper is here. What happens is that when you excite the qubit and change it into a different state, in this case they're saying pi pulse on or off, that means 0 state or 1 state. Then you see there's this dispersive shift, so the readout resonator changes its frequency to something slightly lower. And then for everything here, you're applying signals through the measurement port. If you start to apply a signal through the control port, so directly to the transmon, as they're labeling, or Coaxmon, then you can work out what are the frequencies of your qubit transition. And here's where you see you've got this kind of single photon 0 to 1 shown here. You can create a 2-photon process to work out 0 2 over 2, or 3-photon for the 0 3 over 3. In all these cases, you're revealing the anharmonicity, which is to say that the gap between 0 and 1 is not equal to the gap between 1 and 2, or the gap between 2 and 3. And you need this anharmonicity in order to let you reliably make a 2-level system where you say these truly are 2 isolated energy levels, and this is what you require to actually make any qubit. So now this will hopefully play. Yep. So just to sort of walk through this, there's a video. So you can see we have a chip, which is, in this case, it's about 15, 16 millimeters in size, not always the size that's chosen. There on the top side is our Coaxmon qubit. There is the LC resonator in the coaxial geometry on the bottom of that chip. These are both around 1 millimeter in size. Here you can see how the kind of wiring, which is coaxial, approaches out of plane. Then you can kind of come up with ways to couple these together. So the purple structure in the middle is then a coupling between these qubits. Again, you can then approach with an out of plane wiring for the next. This could be stamped in 1D, so you can scale in 1D, or you can scale basically any way that you want. So you already have something which is intrinsically able to scale in 2 dimensions. Because all the wiring is done coaxially, so you've got that central pin, and now this box was the ground that was coming around this. You've got a signal path which is inherently directional. That means that you're going to suppress any ability to have crosstalk, so any kind of signal connections from one either qubit or resonator to the adjacent qubit or resonator. And then the other thing here is that you see there's no need for things like the wiring to fan out to the edge of the chip. So you know, this really is kind of quite simple and clean to think about. I would make these arguments. The other thing here is that because there's no need to do any bump bonding or wire bonding, this means you can change chips very quickly. So these don't make contact because it's all done at microwave frequencies. So in other words here, you're literally able to kind of either take a chip out, put one in, remeasure it, and there's nothing which is kind of irreversible going on. So certainly with wire bonding, you will always leave some residue when you try and remove these. With indium bump bonding, you do have to be very careful about being able to ever separate those two chips again. That can be quite a kind of irreversible process. Let's put that up the top. Yeah, so just to sort of summarize with this, what I've sort of shown is we've walked through a traditional approach to superconducting circuits, walk through the performance you normally got, how that was sort of sold as saying that superconducting circuits are a really sensible approach, mentioned how this didn't actually help from scalability and you had to introduce new processes, those being things like flip chip to make a multi-qubit module, things like air bridges or through silicon vias, so literally extra fabrication. Then really got around the fact that actually the Coaxmon, when you sort of have this design, you don't need any of those things. You have a design that is inherently able to scale at 2 dimensions. You already have outer plane wiring, so there's no need for any additional kind of features for basically saying how do I wire my signal lines or my kind of readout lines on chip. That's not taking up any space. And all of this you're able to do with a kind of contact-free measurement environment, which ultimately means you can, iterate on devices in a non-destructive way and remeasure the same device if you need, and look at things like aging or something, all without, kind of contacting or destroying the sample. So the thing I haven't quite touched on here is actually the eventual performance of these devices, and the reason I haven't touched on that is because that's research which is imminently due to come out from Leak Lab, and I do not want to steal their thunder. However, I'm very confident to say that they've been able to demonstrate that you really can get a certain performance on single qubits and scale it immediately to a 4-qubit device with no degradation. And that is a statement which has not been possible on any other approach to superconducting circuits. So with that, I'll now pivot us back to some kind of questions relating to working in quantum computing. So here I kind of previously I walked through my career in some very quick steps, but I think there's some kind of just interesting questions that may be just worth mentioning because maybe people in the audience have thought about this and would just find this interesting. So I think the first obvious question is do you need a PhD? And this really is a yes and a no. So there are definitely roles where it is not required, or it's certainly not necessarily the usual way of becoming skilled. So for example, there are people with a software background. This normally becomes something you would learn with kind of on the job knowledge, in other words, leaving with a master's. It can be the case that if you have equally working kind of electronics background or even some clean room work, this is something which doesn't at all require a PhD in order to build that skill set that would then still be ultimately useful in a quantum computing company. That being said, there are some, what most companies label as kind of quantum engineering roles, where what you start to have are really kind of working with cryogenics, kind of quantum information theory, how to do measurements, and these are things which are often only taught within a research environment. In an ideal world, that wouldn't be the only way, but being honest, it often is. In terms of other things which can be very useful, or at least things to point out, certainly on a CV or something. I think that the key one I would really emphasize is actually this bottom one, which is showing interest. A number of times, just simply saying, oh, actually, we have followed the socials, we follow your news, there's this, something's happened, and actually this is really positive. That's something that reflects really well. Other things that can, really sort of matter that are not obvious are things like, hobby work, saying that you've worked with Raspberry Pis and you really like electronics can be, it can certainly make someone, read your CV in a different way or interpret your interest in a different way. Python and programming skills is an absolute must. I think every company without fail would really say that this is true. In terms of, again, how do you get involved and is it the case that if maybe you're doing an undergrad, you're not yet near the end, you're not really sure what you want to do, do internships exist? And the answer really is yes. Are they advertised? Not always. So in any of those instances, you know, get in touch and sort of say what your interests are, say what you'd like to do, and maybe the answer's bad, but maybe it's good. Maybe there's a thing where actually something can be done. So on all this, I'm happy to kind of answer any more questions and you know, get around to this. And I think with that, I've probably spoken for too long. So I'll say thank you very much for your time and attention.
Thanks so much, Jonathan. So yeah, everyone, please just post your questions in the Q&A section. And we already have one question that was posted in the chat. I'll try and give you permission to speak if you want to pose it yourself.
Wait, can you hear me?
Yeah, we can hear you.
Oh, cool, thanks. Thanks for the presentation, actually, that was really interesting. I was just wondering, like, I guess I can just read the question because I've just pasted it on the chat. So like, how is your work on a day-to-day basis? Like so for example, I'm from a more theoretical background in undergrad. So I did a lot of QI then, but then I went on to do a PhD in like a different field that's more computational, but more like condensed matter rather than QI. So I was wondering, like, what is the group structure like at the company? And like, are you gonna be able to do a bit of everything, or like what the learning curve is like when you start, if you want to work more into like the theoretical team and stuff?
Okay, it's a really cool question. In terms, right, let's try and sort of break down a couple of different parts. So would any one person do a bit of everything? Probably depends on you know, company size and company scale. So obviously the smaller the company, the more that's true, you would. In general, I would probably say no. Now, let me just sort of caveat and explain that a little bit, which is that it's always helpful to know a bit of everything, because ultimately you will need to sort of talk and interact with other people, meaning other teams. And in order for you to kind of create a common language and understanding, it's always helpful if sort of both sides know a little bit about one another. So that would be my kind of answer of what would you do in terms of, do you do a bit of everything? I would probably say no. The general intention is that you'd probably like specialize in, you know, one thing. That thing may be quite broad, by the way, but ultimately you're, you know, if you're responsible for you know, nanofabrication and, you know, therefore making the chips themselves, you're probably not also responsible for you know, the software side of how do you physically control the instruments, for example. Because even the software, there's multiple sides, right? You've got the simulation aspect of understanding what devices behave like, but you also have the how do you actually perform measurements. You may do sort of 2 of those. I don't think you'll do all of them. In terms of then, what was your, you know, what does a working day look like? Does depend on the role, but it's also one of those things that's probably not a typical working day. I think most people you ask about this, they'd probably answer and say that one of their favorite things is the variety. And this is very common across, you know, an assortment of people that work in, you know, kind of quantum device or quantum computing type work. There may be certain days, so I'm answering from a quantum engineer perspective, because arguably that would be where my background has been. There would be days where it's spent entirely within the lab, meaning you opened or closed the, you know, the dilution refrigerator, had to mount samples and so on. I have had days where I've done, you know, nothing but CAD work. I've had you know, days where I've thrown my head at trying to sort of make a you know, measurement work or something. So it's the variety is certainly an appeal there. That may not come across as the answer you were hoping for. I'm not saying it to be on the fence. I'm actually trying to describe how it is.
Oh, thank you very much. Sorry, can I just quickly ask a follow-up question on like the software aspect? Because you said that like either you know, usually it's quite specialized, and I totally get that. But in terms, like, if you were to, for example, work mainly into the software stuff, are you using like your own, are you developing your own software? Are you using like things that, for example, I know IBM has like a free thing you can try out online for the quantum computer in terms of playing around with gates and stuff. But like, what's it like at this company?
So there's numerous. So there are different lives. There's different aspects to the sort of software in the end. So you've got things like it really is. It boils down to you want to make a design. If you sort of break this down, ultimately that means you need to make some CAD mask. That doesn't mean you're using CAD's tools to do it. You may do that programmatically within Python. This design you need to sort of simulate in order to understand the frequencies and that you expect to get to compare to a measurement. So now you need to tie that, again, this is software work, to some means of doing simulation, right? You then need to also simulate those things from a kind of quantum understanding, like the Hamiltonians. What is the kind of coupled circuit that you're creating and what are the dynamics of it, which again is a simulation task, but very different to the understanding what frequencies a certain lithographic layout gives you. You've then got the whole sort of measurement aspect of this, where you're saying, I want to implement the following gates. Now, even this you can break down into sort of two different ways. You've got the interfacing with instruments aspect of it. So when I say I perform some operation, how do I know that the electronics is actually doing it? But then you've also got this other aspect, which again sort of ties back to the kind of quantum information side of it, where you go, what is the large algorithm I want to run that is in some way mapped onto a certain number of kind of specific quantum gates? And that is again a sort of theory task, or sort of software task. So I hopefully I'm sort of describing that even under like a software umbrella. I think I've just given sort of 6 quite different facets of it. And it might be that you would interact with several of them, but hopefully I've sort of described that they're all quite different enough that not many people would be able to do all 6.
Yeah, that answers it very well. Thank you. Like, it's basically just a bunch of mini physics projects. And
Yeah,
it sounds quite fun. Cool. Thank you very much.
That's what we like to describe it as. Is quite fun.
Yeah, thanks. I think I can see one more question here. Alexia, I'll give you permission to speak.
Waiting on the unmute, I think.
No, he's in the library. So I'll read out the question. So Alexia asks, if I'm not mistaken, the chip full of Coaxmons allows coupling each qubit to only 4 neighboring qubits. How bad is it? And are there any workarounds?
I mean, strictly speaking, if you go diagonally, you could go to more than 4. So if you just think about putting a grid of 9 and you're asking what can the middle one couple to, the answer is 8, not 4. That being said, so sorry to otherwise that maybe came across a little more bad. I meant it's not always the case you want to couple to more. It's worth pointing this out. So it can be that certainly this is something which IBM has started to publish about, which is that frequency collisions, when you have too many qubits that can couple to more other qubits, can become a really big problem. So being able to specifically address a certain pair becomes very, very difficult. So for that reason, you often don't necessarily want to couple, large numbers to large numbers.
Great, thanks. Yeah, if there's any other questions, feel free to post them in the Q&A section. And I think there's some of the audience has sort of given another answer to the first question that we've had.
Yeah, nothing.
If there's no more questions from the audience, maybe a question for myself, which is what sort of time horizon are we looking at when we're thinking about sort of multiple qubits with high fidelities and high coherence times in the future? I think that's probably a classic and maybe a question that is not liked too much by people in the community, but I think it would be interesting to hear your take on it.
I guess so. Just to, when you're asking this, are you asking because you're sort of the opinion that the answer isn't now?
Well, not necessarily. I wouldn't say I'm super pessimistic, but I think sometimes that maybe it is a bit longer than a lot of people think it is, or than one is made to think by sort of what people are saying.
I mean, okay, that's fair. So I think that ultimately, there would be a large part of the community that would make the argument that the answer to that is now, and that they would say that ultimately demonstrating quantum supremacy says that this is the right technology because it was able to show a sufficient number of qubits at a sufficient fidelity, was able to create a circuit which you couldn't simulate in a reasonable time with a classical computer. Of course, that was a very targeted problem, and a lot of time went into thinking about how to kind of, I don't want to quite say rig the problem, but certainly, try and make as many things in favor of the kind of quantum computer as possible. Now, that's in itself, though, wasn't a bad exercise, because there were some proponents who simply disagreed that a quantum computer would ever win. So even demonstrating limited examples of a win is still fundamentally important, because you need to show that before you can even ask the question of, okay, what useful can you do with this? So that's probably an answer where I'm sort of pivoting towards saying the answer is kind of now. Actually, the performance and fidelity is at a point where you can start doing actual calculations, where really what I'm saying with that is it's no longer like a physics experiment, like a sort of textbook, what kind of interesting quantum optics can I do with a man-made object? That's where the initial demonstrations of things like how large a quantum system can you make and can you control, that's sort of the question that was arguing about. But really, now that you're sort of getting examples of being able to do like Hartree-Fock work, or actually simulating molecules, really, if you're able to do this, you're starting to enter the realm of useful things, and you can only enter the realm of useful things when you've got a high number of qubits at a high fidelity. Tying it back to your kind of question.
Yeah, no, I think that's definitely a reason for being quite optimistic. So yeah, thanks. That's good. Yeah, I guess I was referring back to the my question also ties into the fact in that when do you think we'll have the hardware that can really perform sort of very useful and complex calculation? Because I did think as well that the Google quantum supremacy paper was a groundbreaking result, but then the problem they were solving was very much engineered to be solved with the kind of quantum computer they were building.
So for me, a really fun spin on the question you just asked, right, is and this kind of comes from a metrology perspective, right? So a metrology perspective would say, what's a classic metrology problem is telling the time, and if you tell the time, okay, I make a clock, right? But how do you know if that clock tells the time reliably? You make another clock and compare it to it. But say those two clocks don't agree, have you got one that runs fast or one that runs slow? So now you have to build a third clock and run all the permutations. My point there is that an interesting perspective of saying, okay, what if a quantum computer can do something useful? Useful really means something that a classical computer cannot do. And I agree with you on the not meaning some limited targeted problem, like actually something a bit grander than that. However, once the quantum computer goes, oh, here's your answer, how do you know that was correct? Right? You're going to need to run the same problem into a second quantum computer to see if that gives you the same answer again. So you've got this kind of classic clock metrology problem that will also exist.
Yeah, no, that's a very, very interesting take on it. And I think it just shows that not only people with a quantum background can contribute meaningfully to the future of quantum computing, and there'll be people with backgrounds from very different areas of physics which will have very useful input. That also ties into the comment from one of our listeners, who said that, I think, yeah, Oxford Quantum Circuits have hired straight out of BSc with no quantum background.
Yeah, I think this statement needs to be made many times over. There's a pragmatic element to it, which is if you could only hire people that have done a PhD in something relating to a qubit or something. Simply put, there's not enough of them in the entire world. So all companies need to go and look at wider pools because there just aren't enough people to hire. But more generally, that's not helpful because there's no diversity of the thinking process there. So you really do need people from all kinds of backgrounds. This is an absolutely genuine statement.
We also have another question, and I'll give permission to Apurva. Sorry for the poor pronunciation.
No, it's fine. Thank you so much for the really nice talk. So my question is basically that, I basically come from, and I wanted to ask, like, for us, most of the times things don't work, so like we spend a lot of time debugging and things like that. So I wanted to ask, like, how does it feel like an academic background? So how did it feel for you to switch in the beginning?
Sorry, you cut out a couple of times there. You're asking how did it feel to pivot from a kind of research background of sort of debugging problems, and how was the transition to a commercial background? Is that the
Yeah,
question?
exactly. Yeah.
Right. Okay, yeah, that's a really good question. So I think one of the so at its best, the academic background gives you this ability to kind of go, what's a really interesting problem, and how do I kind of think about it? And this problem doesn't necessarily have to be grounded in terms of like, is
Yeah.
it useful or something, right? The problem with that, and that's described at its best, is it also means you really don't define that problem.
Mm-hmm.
So it can be very hard to sort of go, when did you achieve it, right?
Yeah.
If you look at most kind of papers that get published, there can be months and months of work that went into it, but the actual like actual plots that are literally there in that paper and the actual data sets themselves, they might be only a week's worth of work where everything aligned, right? And many papers they kind of are either not enough for their purpose or they're too much for their purpose, right? And which really comes back to what I'm saying. It's not a well-defined. The scope of the work isn't actually well-defined. Where you say, have we ticked this goal? Yes, no.
Yeah.
In a commercial environment, this kind of, I guess I'll say, like kind of road mapping or kind of like idea of coming up with what's the objective, what's the thing you're trying to do, how do we do it, how do we assess we do it, how do we measure and know, and so on. This whole process is really, I'd say, broken down in a far more useful way, which sort of lets you go, okay, yes, you're solving problems. I can't say we don't have to do that. But also you only solve the problems that you sort of need to, because you're not sort of working to some completely open-ended problem where it then becomes easy to kind of foresee problems that aren't actually a limitation to you. So it kind of lets you get off of that that cycle or off of that rail very quickly and kind of get back on and say, I've solved the important thing. Now let's make some progress.
Yeah, that was really helpful. Thank you.
Great, thank you. Yeah, maybe any other questions? Just feel free to post into the Q&A or the chat. But we're also approaching the hour, so if there's no more questions, thank you so much, Jonathan, for joining us. That was very, very interesting, and yeah, leaves us being very optimistic that we have some very competent people working on next generation quantum computers right here in Oxford. And yeah, thanks for everyone for taking the time and tuning in. And hopefully that was also a useful introduction to sort of the commercial quantum computing hardware sphere. And yeah, maybe some of you are interested in working in the sphere, and that has really sparked your interest. Yeah. So thanks a lot. And yeah, have a great last week of term to everyone that's in Oxford.
Yeah, no, thank you very much for the opportunity. Indeed, yeah, hopefully everyone found it interesting, enjoyable, maybe even both.
Yeah. Yeah, thanks so much. Yeah, have a great day, everyone. And I'll see you. Bye.
Yeah, cool. All right, have a good evening. Bye.
Have a good evening. Bye.